Okay, question 12 part 8 is a proof question. We've got to prove that 1 minus cos 2 theta is the same as tan theta sine 2 theta. And there's a few ways to do this. I always prefer to turn what they give you on the left into what they give you on the right, which is a little bit tricky here, but that's what I'll show you. First thing to do is change the cos 2 theta. Cos 2 theta is 3 different things. You can write cos 2 theta as cos squared theta minus sine squared theta, or you can write it as 2 cos squared theta minus 1 by changing the sine squared theta into 1 minus cos squared theta, or you can write it as 1 minus 2 sine squared theta by changing the cos squared theta into 1 minus sine squared theta. I'm going to use this one because there's a sine in the answer. So this, when we expand it, the ones cancel and this becomes negative 2 sine squared theta, which is just 2 sine squared theta. Now the next bit is a bit forced really. I know I need to get some tan thetas into the equation, and the only way to do that with a sine squared theta or a sine theta is to introduce something to do with cos theta, because we know that sine theta over cos theta is tan theta. But I can't just times this by cos theta or divide it by cos theta, because that's going to change its value. So what I can do is times by 1. But my 1 is going to be disguised as cos theta divided by cos theta. So I've not changed the value of this because I'm timesing by 1. What that now allows me to do is introduce a tan theta, because I've got a sine theta divided by a cos theta. So that's going to be a tan theta. Then I've still got a sine theta left and another cos theta on the top. What I've got now is a tan theta times by 2 sine theta cos theta. And 2 sine theta cos theta is my double angle formula for sine 2 theta. So a little bit sneaky, a little bit forced, but gets us what we need. Okay, in part B, this big 6-mark trig equation question looks really scary and complicated to begin with, but if you look at what we've got in here, we've got 1 minus cos 2x, and that's what we proved in the first part is equal to tan x sine 2x. So that's what I'm going to do first. I'm going to replace that second bracket with tan x sine 2x. And the reason I'm doing that is because if you look at the right hand side, there's also a tan x sine 2x here. Now, never ever ever divide by a trig function in the same way that you would never ever ever divide by an x. Rather than dividing by an x, you would factorise an x out, because when you divide by a variable, you lose the solution x is equal to 0. Rather than dividing by tan x sine 2x here, we're going to subtract this from the right hand side and factorise it out. So I'm not going to expand these brackets yet. So when we take out the tan x sine 2x, from here, this term, I'm going to get sec squared x take 5 because if you times those two things together, you get this. When I take out a tan x sine 2x from here, I'm going to be left with minus 3 tan x. Again, if you times these two things together, the tan x sine 2x times this, you'd get this term here. So that's it factorised out. So we've then got this term or this term needing to equal 0. So either tan x sine 2x is equal to 0, or this big bracket here is equal to 0. Let's deal with this first. If this is equal to 0, and you think about the graphs of tan x and sine x between what's the range? Between minus pi over 2 and pi over 2. If it's equal to 0, the only solution we're going to get is that x is equal to 0. The other solution that would come from here, being pi, but then dividing by 2, so pi over 2, is just outside the range. It's not all equal to, so it's not in the range, so it's just x equals 0 from this section. So that's all that dealt with now. We've just got to solve this to finish off the question. So that's what we're going to concentrate on next. I don't actually need the brackets there. That's a 3. 3 tan x is equal to 0. Now to solve this one, we need to use the identity that links sec squared x and tan x, which is that tan squared x plus 1 is equal to sec squared x. If you forget that one, you can get it from just your sine squared plus cos squared is equal to 1 relationship, just by dividing each term by cos. I often forget which way around the plus needs to go, whether it needs to be with the sec squared or the tan squared. So I often just divide this one, which I know really well, by cos squared, which gets us to here. Sine squared divided by cos squared is tan squared, cos squared divided by cos squared is 1, and 1 over cos squared is sec squared. So we can swap this sec squared x for 1 plus tan squared x, or tan squared x plus 1. Minus the 3 tan x, let's do it in that order, minus 5 is equal to 0. Okay, let's get rid of this. So let's put the, this is a stealth quadratic. It factorises. You could let tan x equal y if you wanted, but you don't really need to. It's going to be a 4 and a 1. It's going to be a negative 4 and a positive 1. So tan x is equal to 4, or tan x is equal to minus 1. So x is the inverse tan of 4, making sure you're in radians. Is 1.33, or inverse tan of negative 1 is minus pi over 4. Just remembered it said 3 decimal places for the give any non-exact answers to 3 decimal places, so I need another decimal place for this. So if I just press up on my calculator, it was 1.326. 1.326 to 3 significant figures, 3 decimal places. So those are our 3 answers. Don't need to look for any other answers because the range was only minus pi over 2 to pi over 2. The next value would be outside of the range.